This video shows the Mechatronics system's role values which help you to create and validate complex mechatronic systems. The first example deals with an electric car development. From requirement engineering to multi-physics simulation using Modelica. All necessary requirements and parameters for the car are captured and managed on the 3D Experience platform. For instance, the acceleration of the car with its duration from 0 to 100 kilometers. Requirements and the parameters are available for engineers. It's the same for the system's architecture views. They can be linked together and reused as rules and checks during the development phases. Systems behavior is designed with Modelica using the CATIA Dymola behavior modeling application. Vehicle templates with high-fidelity models can be captured and reused. For instance, the full active suspension system is defined up to the component level by combining all the disciplines including electric drives, power electronics, vehicle dynamics and control. You can easily come to a solution. Then the results such as maximum torque can be reused as inputs for 3D design templates, which for example precisely define the gearbox. The role takes advantage of the powerful 3D modeling capabilities of CATIA Mechanical. Modelica models from 3D kinematics are also available to rapidly define the actuation and control laws of the Mechatronics system. In this example, it is applied to the automatic car door opening. 3D Experience helps to develop complex systems with Modelica and FMI open standards, associative to 3D modeling. It provides system definition unicity, systems engineering reuse, and consistent systems engineering methods. Thus, it helps in achieving fast and complete convergence between multiple engineering domains. We will learn to create a simulation of a simple 4-bar mechanism. We use 4-bar mechanism in car wipers, rear double wishbone of cars, etc. This demonstration will empower the modeling and simulation engineers to leverage the power of Modelica and the 3D Experience platform. This helps them to rapidly develop, simulate and validate simple and complex mechatronic systems. Mechatronics is at the heart of almost all complex systems. Most of the mechanisms are actuated by electrical or hydraulic actuators, with sensors and controllers. These complex systems typically consist of a combination of mechanical, embedded control software, electronic, hydraulic and pneumatic technologies that interact with each other. This demonstration will give modeling and simulation engineers a global understanding of the multidiscipline system's behavior on a single platform and help them to quickly develop and assess the optimal solution. We will create behavior of DC motor with the PID control, using Modelica blocks to actuate the 4-bar mechanism. This simulation implements the mathematical models of all components of the system like linkage, transmission, electric motor and control devices. We will perform simulation to optimize dynamic performance. Accurate tuning of the PID control makes it possible to obtain a good dynamic performance. We will perform 4 simple steps to create the simulation. Let us view the kinematic design and animation. The physical product contains the CAD geometry from the conceptual design and the mechanism definition. A set of engineering connection and joints defines the kinematic mechanism. With the different mechanisms interacting with each other, it is possible to manage very complex mechanical systems. The mechatronics engineer can do a first-level verification and validation of the mechanism by animating the kinematic model. This helps you to easily perform kinematic analysis. The engineer can check for visual inspection, clashes, interferences and movements of the assembly and then validate as design. The system architect can now create the system architecture of the complex system by defining the requirements, functional architecture, logical architecture, allocations, interfaces etc. To save time, engineers can reuse previously designed logical architecture. We have already seen how our FLP approach can be used. In the second step, we will create Modelica representation of mechanism. Mechatronics systems engineers can rapidly develop, simulate, and validate complex mechatronics and cyber systems. mass and center of gravity of every 3D CAD model is automatically calculated and considered for generation of mathematical model. With a few more clicks, the platform enables the mechatronic system engineer to create the modelica representation of the mechanism. This is a unique capability, wherein the platform combines the power of the CAD mechanical apps which are used to design the physical product, along with the power of open-source modelica language-based CAD behavior modeling which is used to define the behavior of a mathematical model. With this combination of capabilities, it is easy to represent the existing 3D physical data in the mathematical model. In the modelica representation of the mechanism, it is possible to recognize the kinematic chains, axis, joints and the kinematics loops. The mass, the inertia, and the center of gravity of each part are fetched directly from the 3D model. In the next step we will view the behavior modeling of motor with feedback control. The platform also enables the mechatronic systems engineer to design PID, proportional integral derivative, controller-based control logic to drive the mechanism. Modelica Standard Library, MSL, contains all necessary components to design such controller. It is possible to develop mathematical models for control logic algorithm like controller, for motors like DC motors, and for power sources like power electronics. A PID controller continually calculates an error value as the difference between the desired set point and a measured process variable. It then applies a correction based on proportional, integral, and derivative term denoted P, I, and D respectively. Hence, the name. Mechatronics engineer adds mathematical model for controller, DC motor and power electronics. The engineer can then change the parameters of these models. Mechatronics engineer can create a separate library for mathematical models of such components and use it directly in the mechanism. By adding such desired components from the libraries, you can easily optimize existing systems. Different controller designs like PI, PD and PID control can be tested. PID values have to be tuned to obtain good dynamic performance. Physical product can be modified after simulations. We will now create logical connections using interfaces. We will connect the PLM connector and CAD behavior modeling connector. We will introduce the DC motor model consisting of PID control to the whole system by making the necessary connections. Let us run the simulation. In the execution setup, configure the start time and stop time. Configure the output interval and integration. Click Simulate and then click Play. Finally, you can select the signals to plot and to observe simulation results. Based on these results you can make the necessary modifications to adjust the behavior of the system. Today, many different tools for control modeling, 3D modeling, and multi-physics are applied without a strong integration. Mechatronic systems are made in silos, where the solutions have to be found in a systematic approach, control can be tuned, mechanical systems have to be modified, etc. With Mechatronic Systems Engineer role, in 3D Experience Platform, Dassault Systems provides a single environment to design, experiment and optimize your mechatronic systems, which can be used all along the design chain, from conceptual engineering up to detailed design.